Hi everyone. Today I want to talk about the purely inseparable extensions. But before I really introduce the purely inseparable extensions, I want to recall the concept of separable extensions. So let F to be a field and let E over F be an algebraic extension. We see E over F is a separable extension if for every alpha in E, the minimal polynomial of alpha over F is a separable polynomial. Note that when we say some polynomial is separable, it means it has distinct roots. Or in other words, the polynomial and its derivative has no common root. Okay, so it's important to note that every algebraic extension of a field of characteristic 0 is always separable, and every algebraic extension of a finite field is also always separable. So when we talk about like the purely inseparable extension today, what we really want to focus is on the fields which are infinite and with like non-zero characteristics. So you may ask, why is a separable extension so important? The answer is the existence of inseparable extension is actually the main obstacle for extending many theorems proved in characteristic 0 field to non-zero characteristics field. So for example, we have learned about like fundamental theorem of Galois Theory. And that assumption is that the extension should be normal and separable. But in fact, the theory itself is originally a theory about normal extensions for the field with 0 characteristic. But once we have the separable assumption, we can extend that to the field with non-zero characteristic. And here are some motivating questions. So what about the extensions that are not separable? What properties do they have? And what are their relationships with separable extensions? So we first define what is a purely inseparable extension. Let F be a field and see that E over F is an algebraic extension. We see E over F is purely inseparable if for each alpha in E, the minimal polynomial of alpha over F has only one distinct root, which is like exactly the opposite to the separable extension. So this definition is not enough, so I will extend this definition to a set of like equivalent statements. I will not provide any proof here because this is very straightforward, but if you are interested, you can also like talk with me. What's really important here is statement 3 and 4. That says like if E over F is a purely inseparable extension, then like it's actually if and only if. Yeah. For every alpha in E, alpha to power there exists some n such that alpha to power of p to power of n is in F. And the minimal polynomial of alpha over F is equal to x to power of p to power of n minus alpha to power of p to power of n. So we will use this two definitions over again like later, and this is actually a more like common definition like most mathematicians use. And here is the important remark, which you can also see this as an example about like how can we find a purely inseparable extension. So let P to be a prime and let F to be a field of characteristic. We consider one element T in F, and we can get a purely inseparable extension by adjoining the piece root of T. Of course, this is based on the assumption that like the piece root of T is not already in the F. So by lemma 2.1.2, we can see fx equal to x to the power of p minus t is irreducible. Therefore, it is a minimal polynomial for the piece root of t. Then we can consider the E, which is the simple extension generated by the piece root of t, is actually a field. For every element alpha in E, we can write it as like linear combination of power of piece root of t, where AI is in F. Then by some algebra and using the fact that characteristic of F is P, we can get that alpha to the power of P is equal to A0 to the power of P plus A1 to the power of P times T plus blah, 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 plus A P minus 1 to the power of P times T to the power of P minus 1. And obviously this thing is in F. So we can conclude that E over F is purely inseparable. And here is a more concrete example. I didn't have like every detail here, but I think this is an interesting example. So let P be a prime and consider the finite field of P element Fp. E is a field like Fp joint T, and F is a field Fp joint T to the power of P. We claim that E over F is actually a purely inseparable extension, since for every alpha in E, alpha to the power of P is in F by the same arguments in the above remark, like using the same method here. And then, like a more intuitive way we can see that is like we can observe the minimal polynomial of T over F. It should be x to the power of P minus T to the power of P. And because the characteristic of field Fp is equal to P, that is the same as x minus T to the power of P. And this minimal polynomial only has one distinct root. And then we want to talk about some properties of purely inseparable extensions. This one is a really simple one. It just says like if K over F and L over K are both purely inseparable, then L over F is purely inseparable. Like the proof is also very straightforward, just using the definition of like purely separable extensions. This one is a more important one and more like interesting one. So let E over F to be an algebraic extension, and there exists a unique field except such that except over F is separable and E over except is purely inseparable. In other words, any algebraic extension can be uniquely decomposed into a separable extension followed by a purely inseparable extension. One important remark here is that except for any extension is always a set of elements of E which are the separable over F. So before the proposition, we need to introduce the lemma. So lemma 2.2.3, which is like basically exactly the same as our homework 7 problem 3, but with a little bit more detail. So I will not like go through it, but you can have a look of it and we will use it. Okay, and then we can prove the proposition 2.2.2. If the characteristic of F is 0, we can just set except to be E, and we are done. If the characteristic of F is like some prime P, then we can let except to be the set of elements of E which are separable over F. First, we show that except over F is separable extension, and this is obvious by the definition of except. Then we just need to show 2. We want to show E over except is purely inseparable. So take any alpha in E. We want to show there exists some n such that a alpha to power of P to power of n is in except. In other words, alpha to power of P to power of n is separable over F. So let M to be the minimal polynomial of alpha. If alpha is separable over F, then we are done because we can just choose n equal to 0. So we only need to consider the case where like alpha is inseparable over F. For homework 7 problem 3, we know like if alpha is inseparable over F, then like the derivative of mx is a 0 polynomial. Then again by lemma 2.2.3, we know there exists some irreducible gx such as mx equal to gxq, where q is a power of p. Because q is a power of p, we can let like q to be like over p over n that we want. And then we can show like alpha to power of p to power of n is separable over F. This is because like G will like now be the minimal polynomial of alpha to power of p to power of n. And since gx and dgx are relatively prime by our lemma, it is separable. Hence, we can conclude there exists some n such that a to power of p to power of n is like in the except. Therefore, E over except is purely inseparable. And in the end, there are some definitions like based on the proposition. So the integer except to F is called the separable degree of extension, and E to except is called the inseparable degree of the extension. There are some properties of this extension, but I don't think we have time to cover this today. But I think this is in the Dominic book, and like there are also some information online. And here is my bibliography. So that's it. Thank you so much.